Welcome to the Deep Dive. Today we're taking a really fascinating look into the world of fiber optics. Specifically, we're doing a deep dive into Fiber Optics 101, Basics and Cabling. Now, this isn't just any general overview. We're actually breaking down key insights from an Intelligent Transportation Systems Masterclass. It's a multi-part educational resource, and this is important. It was created and presented by Atkins Realis. It was developed specifically for the Florida Department of Transportation, FDOT. It's frankly an incredibly valuable resource if you want to get up to speed quickly on this critical technology. So our mission today is kind of threefold. First, we want to really understand how fiber optic technology actually works, the nuts and bolts. Second, we'll get some perspective on why the Department of FDOT chooses to use fiber optic communications in their projects. What are the advantages? And finally, we'll dig into what specific types of fiber optic cabling you'd typically see used in a construction project installation. And you'll hear how the stuff we talk about, it's directly rooted in FDOT's own design manuals and standard specs. So it's real-world application. Okay, to get us started, maybe you could walk us through some of the absolute basics, like the building blocks of digital communication that underpin all this.
Absolutely. And yeah, the material Atkins Realis put together for FDOT, it's very thorough. Before we jump into light pulses and glass threads, it's probably worth doing a super quick refresher on the very essence of digital communication. We're talking bits. Binary digits, the smallest possible unit of information. Just think of it simply as a 0 or a 1, an on or off switch, a yes or a no. Now, when you group 8 of those bits together, you get a byte, B-Y-T-E. And the byte, that's really the main unit we think about for communication speed or throughput. Sure, there are bigger collections like words for more complex stuff, but understanding the bit and definitely the byte is key here. Because this whole binary idea, these zeros and ones, it maps directly onto how fiber optics work.
Okay, got it. Bit is on or off, 0 or 1. Group 8, you get a byte. So with that foundation, let's connect it to the core definition. You said fiber optics uses glass threads to transmit high-speed pulses of light-carrying information. So how does that become these zeros and ones? How's that translation happen?
Yeah, it's actually a pretty elegant process when you break it down.
Okay.
So first you've got your data. It gets fed into a transmitter, which is the source, right? This transmitter, it's got an LED or more commonly for long distance, a laser inside. What the transmitter does is it translates that incoming data into a sequence of bits, those zeros and ones we talked about. It does this by literally turning the light source on for a 1 and turning it off for a 0, flickering incredibly fast. These light pulses, these flashes, are then sent down that super thin fiber optic strand. They travel really fast, maybe about 2/3 the speed of light in a vacuum, until they hit the receiver at the other end, the destination. The receiver has a special light detector, like a photocell. It senses these individual pulses of light, and once it receives them, it does the reverse, converts that series of ons and offs, those zeros and ones, back into usable data for whatever networking equipment is connected.
Okay, so light on is 1, light off is 0. Simple enough in concept. But how does the light stay inside that tiny glass thread over potentially miles? Does it just shoot straight?
Good question. No, it doesn't just shoot perfectly straight without help. It uses a physics principle called total internal reflection. Think about the fiber's core, that central glass pathway. It's surrounded by another layer of glass or plastic called cladding. This cladding layer is designed to be highly reflective, almost like imagine lining the core with incredibly thin tinfoil, metaphorically speaking. So as the light pulse travels down the core, if it hits the boundary between the core and the cladding at a shallow enough angle, it bounces off. It reflects back into the core. It just keeps bouncing, reflecting inward, zigzagging its way down the fiber, effectively trapped inside. It's a very efficient way to guide light.
Wow, okay. So the cladding is like mirrors lining the pipe. That bouncing pathway sounds like it needs to be perfect then. What happens if there's like a crack or a sharp bend?
Exactly. You've hit on a critical point. That pathway must be continuous and relatively straight, or at least gently curved. No sharp bends. If there's a break, obviously the light stops. But even a bend that's too tight can cause light to hit that cladding boundary at too steep an angle. If that happens, it won't reflect. It'll actually escape out of the core. It's called attenuation or signal loss. And remember, we're sending a precise sequence of zeros and ones. If light escapes, you lose bits. A lost on pulse means a 1 becomes a 0. A lost off gap might get misinterpreted. So yeah, losing bits means the data that arrives isn't the same as the data that was sent. You get errors, corruption. A clean, continuous line is absolutely essential.
That makes perfect sense. The integrity of the pathway is paramount. Okay, so we have the amazing tech. Data is light, bouncing down a glass thread. Now let's shift to the why. Why is this technology so attractive, especially for things like FDOT's intelligent transportation systems, roadside cameras, message signs, all that? What are the big advantages it has over, say, traditional copper cables?
Right. And for these big infrastructure applications, the advantages are pretty significant. There are several key ones. First up is higher speeds and longer distance. We mentioned light travels fast. In fiber, it allows data transmission over many, many miles, far, far further than you could reliably send an electrical signal down copper without needing repeaters.
Okay, speed and distance, that's huge for covering large road networks. What else?
Second, greater bandwidth. This is massive. A single fiber optic cable can carry, orders of magnitude more data at the same time compared to a similar sized copper cable. Think thousands of times more throughput. This is crucial when you're dealing with, high definition video from traffic cameras, real-time sensor data, controlling multiple signs. You need that capacity.
Right, the sheer volume of data nowadays.
Exactly. Then there's better reliability. Fiber is made of glass or plastic, which are insulators. They're dielectric. That means they don't conduct electricity. So first, it's safer for people installing or working near it, especially around power lines or during lightning storms. And second, it's completely immune to electromagnetic interference, or EMI. Things like nearby power lines, radio signals, even lightning strikes that can corrupt data on copper cables. Fiber just doesn't care. It's also less affected by temperature changes.
Ah, okay. The non-electrical nature is a big plus for reliability outdoors.
Definitely. And finally, it's inherently more secure. Because the data is light trapped inside a glass strand, it's incredibly difficult to tap into without physically cutting or damaging the fiber. And if you do that, the signal loss is usually detectable immediately. Unlike copper, where you can sometimes passively induce a current to eavesdrop, you can't really do that with light in a fiber.
Speed, bandwidth, reliability, security. Sounds almost perfect. You mentioned earlier there's a downside, though.
Yeah, there's always a trade-off, right? The main one is cost. Fiber optic cable itself, the specialized equipment needed to transmit and receive the light signals, the connectors, the splicing, it's often significantly more expensive upfront than installing copper. The installation also requires more specialized skills and tools, so the initial investment can be higher.
Okay, cost. Makes sense. But for critical infrastructure like FDOT needs, those benefits probably outweigh the initial cost in the long run.
That's generally the calculation, yes. The performance, the longevity, the reliability often justify that higher upfront cost for something like an ITS backbone.
All right, that leads us nicely into our third objective.
Okay.
We've covered the how and the why. Let's get physical. Let's talk about the what. What actually goes into these cables? You used the analogy of Russian nesting dolls earlier. Let's start peeling back the layers, starting from the very center.
Perfect analogy. Okay, so at the absolute core, the smallest unit is the individual fiber itself. And we need to stress the scale here. Each single fiber is roughly the diameter of a human hair. Maybe around 125 micrometers, including the cladding, but the light-carrying core is even smaller.
Wow, human hair thin.
Yeah, so you can imagine handling these during installation or repair requires incredible precision and care. They are fundamentally strands of glass. Now, each individual fiber strand has three main parts. In the very center, you have the core. This is the pathway the light actually travels down, usually high-purity silica glass. Surrounding the core is the cladding. That's the reflective layer we talked about, the one that keeps the light bouncing inside the core using total internal reflection. And then, wrapped around the cladding, there's a protective coating, usually 1 or 2 layers of acrylate plastic. It's just a basic buffer to protect the delicate glass from abrasion or microbending.
Core, cladding, coating. Got it. Are all fibers basically the same, or are there different types even at this tiny level?
Good question. No, there are 2 main categories of optical fiber, and it's a really important distinction, especially for ITES. They are single mode and multimode. Now, for intelligent transportation systems, like what FDOT uses, single mode fiber is pretty much the standard. It's dominantly used. Single mode has a very small core, maybe only 9 or 10 micrometers in diameter. Because it's so small, it only allows a single path or mode of light to travel straight through, generally generated by a laser. The big advantage is it can transmit signals over incredibly long distances. We're talking tens, even up to 100 kilometers or more, and it supports very high bandwidth. The downside, the lasers and precision alignment needed make it more expensive.
Okay, single mode for long distance and high bandwidth, like a highway backbone. What's multimode then?
Multi-mode fiber has a significantly larger core, typically 50 or 62.5 micrometers. Because the core is bigger, it allows multiple paths or modes of light from less expensive light sources like LEDs to bounce around inside simultaneously. The pros: It's generally easier to install, the connectors are less sensitive to alignment, and the LED light sources are cheaper than lasers. The major con. All those different light paths travel slightly different distances as they bounce, causing the light pulse to spread out over distance. This limits both the achievable distance, usually only a few hundred meters to maybe a couple of kilometers, and the bandwidth compared to single mode.
So multi-mode is more for shorter runs, maybe inside a building or campus, but single mode really rules for the long-haul stuff FDOT needs.
Exactly. Single mode is the workhorse for telecom and ITS backbones.
Okay, so we have these tiny single-mode fibers, core, cladding, coating, but you don't just run a single hair-thin fiber, right?
Yeah.
How do they bundle these up?
Right, you definitely don't run just one. Sticking with our nesting dolls. The next layer up is the buffer tube. A buffer tube is essentially a small plastic tube that holds multiple individual fibers. Typically, it can contain anywhere from 2 up to 12 fibers, sometimes even 24, but 12 is very common. These tubes serve to organize the fibers, protect them further, and make them easier to handle during splicing and installation. You're dealing with a tube instead of dozens of individual strands.
Okay, tubes with fibers inside. How do you know which fiber is which inside the tube?
That's where color coding comes in. It's absolutely critical. There's a specific industry standard, TIA 598DA, that dictates the color sequence for the individual fibers within a buffer tube. Is a 12-color sequence: blue, orange, green, brown, slate, which is gray, white, red, black, yellow, violet, rose, pink, and aqua, light blue. So fiber number 1 is always blue, number 2 is orange, number 12 is aqua. This sequence repeats if there are more than 12 fibers somehow grouped, but usually a tube stops at 12. This isn't just for fun, it's essential for technicians to quickly and accurately identify the correct fiber when they're making connections or repairs, especially in a large cable with potentially hundreds of fibers.
Blue, orange, green, brown, slate, white. Okay, I see. That standardization is key. So because tubes usually hold 12 fibers, does that affect how the overall cables are structured?
Absolutely. It directly leads to the common fiber counts you see in cables. Since buffer tubes typically hold 12 fibers and then the buffer tubes themselves are bundled together inside the main cable, the total fiber counts almost always come in multiples of 12. That's why you see standard counts like 12, 24, 36, 48, 72, 144, 288, and so on. You're very unlikely to find, say, a 50-count fiber cable. It's all based around that 12-fiber grouping standard.
Makes sense. 12 fibers per tube, then group the tubes. You mentioned a brain exercise earlier from the source material about finding the 61st fiber. How does that work with the colors?
Right, it's a good way to illustrate the system. So if you have a cable with many fibers, say a 144 count cable, that means it has 12 buffer tubes, and each tube has 12 fibers inside. 12 by 12 equals 144. Now, not only are the fibers inside each tube color-coded blue through aqua, but the buffer tubes themselves are also color-coded using the exact same TIA 598-D sequence. The first buffer tube is blue, the second is orange, the third green, and so on, up to the 12th tube being aqua. To find the 61st fiber, each tube holds 12. 5 tubes would hold 5 by 12 equals 60 fibers. So the 61st fiber must be the first fiber inside the 6th buffer tube. What's the color of the 6th tube following the sequence? Blue, orange, green, brown, slate, white. So it's in the white tube. And what's the color of the first fiber within any tube? It's always blue. So the 61st fiber is the blue fiber within the white buffer tube. It's a system to pinpoint any single fiber out of potentially hundreds.
I see. Color code for the tube, color code for the fiber within the tube. Clever. What if you have more than 144 fibers? More than 12 tubes?
Good point. For cables exceeding 144 fibers, meaning more than 12 tubes, they use a striping method. The color sequence for the tubes starts over, but the second set of 12 tubes, tubes 1324, will have a black stripe added. The third set, 2536, might have a yellow stripe, and so on. Same color sequence, just with stripes for higher counts.
Okay, layers upon layers. Fibers in tubes, tubes in the cable. What else is inside that main cable jacket besides the buffer tubes?
Right. The final doll in our nesting set. Besides the buffer tubes containing the fibers, there are several other important components packed inside that outer sheath or jacket. There's usually a central strength member. This is often a solid rod of fiberglass or similar material right in the middle. Its job is to provide tensile strength and rigidity to the cable, so you're not pulling directly on the fragile fibers during installation. You'll often find water-blocking material. This could be a special gel filling the gaps, though gel-free designs are becoming more popular, or water-swellable tapes or yarns. Their job is to prevent moisture from getting in and migrating along the cable if the outer jacket is breached, which could cause damage or freezing issues. There's usually a rip cord, which is a strong yarn placed just under the jacket. You can nick the jacket and then pull the ripcord to easily tear it open for access without damaging the insides. Sometimes you'll find additional strength yarns, often made of aramid fiber like Kevlar, bundled with the buffer tubes for extra pulling strength. And then finally, encasing everything is the outer sheath or jacket. This is the tough outer skin, usually made of polyethylene, providing overall protection from the environment, abrasion, UV light, etc. It's also where important information is printed, like the manufacturer, fiber type and count, date, and footage markers.
Wow, okay. Central strength member, water blocking, ripcord, extra yarns, and the outer jacket. It's way more than just glass strands in a tube.
Yeah.
So with all these components, you mentioned different environments earlier, that must mean there isn't just one type of finished cable construction, right?
Exactly. The overall construction varies quite a bit depending on where and how the cable will be used. Let's touch on the main types relevant here. The most common type you'll see for Department of Transportation, like FDOT or other outdoor municipal projects, is loose tube cable. In loose tube, the coated fibers lie loosely within those buffer tubes, often surrounded by that water-blocking gel, or using dry water-blocking elements. This design allows the cable to expand and contract with temperature changes without stressing the fibers, making it ideal for harsh outdoor environments. FDOT specifically often calls for gel-free loose tube now due to maintenance considerations with the gel.
Okay, loose tube for outdoors allows for expansion. What else?
There's tight buffer cable. Here, each fiber has its coating plus an additional thicker buffer layer applied directly to it. These buffered fibers are then stranded together. It's generally more flexible and rugged for handling, but less forgiving of temperature swings. It's mostly used for indoor applications like patch cords or runs within buildings. Critically, tight buffer is not used for FDOT projects.
Got it. Loose tube for FDOT outdoors, tight buffer for indoors, but not FDOT. Any others?
Yeah, a couple more worth mentioning. Ribbon cable is an outdoor type where fibers aren't loose in a tube but are actually laid out flat, side by side in rays of typically 12, forming a ribbon. Multiple ribbons are then stacked. This allows for very high fiber density in a small diameter cable and enables very fast splicing because you can splice a whole 12 fiber ribbon at once. You often see this used by big telecom providers like AT&T or Comcast for their main distribution lines. Again, not typically used for DOT jobs, but you might encounter it in shared conduits.
High density, fast splicing, but not for FDOT usually.
Okay. Then you have armored cable. This is typically a loose tube cable designed for direct burial underground without needing conduit. It has an additional metallic layer, usually corrugated steel tape, wrapped around the cable core but underneath the outer jacket. This armor provides extra protection against crushing forces and, importantly, damage from gnawing rodents. Rats, squirrels, gophers love chewing on buried cables. A key point with armored cable. Because it contains metal, it must be properly grounded at termination points for safety, as it could conduct electricity if damaged or near power lines.
Right. Armor for direct bury and rodent protection, but needs grounding. One more.
Last one is aerial cable. As the name suggests, this is designed to be strung overhead between poles. It often looks like a figure 8 in cross-section. One part is the fiber optic cable itself, usually loose tube, and attached alongside it is a strong steel messenger wire. This steel wire bears all the tension from the cable's own weight, the dead load, plus environmental loads like wind and ice. This ensures the fragile glass fibers inside the cable part are never put under tensile stress.
Figure 8 for hanging on poles. Steel wire takes the strain. Makes sense. Now, across all these types, especially when installing them, you mentioned bending is a huge concern. Can you elaborate on this minimum bending radius?
Absolutely critical concept. It's possibly the single most important handling precaution for fiber optic cable. Remember, the core is glass. Glass doesn't like to be bent sharply. The minimum bending radius is the smallest radius you can bend a cable to without causing damage or excessive signal loss. If you bend it tighter than this specified limit, you can cause two types of problems. Microbends are tiny kinks or imperfections forced onto the fiber, and macrobends are larger, visible bends. Both cause light to escape the core, leading to signal attenuation or loss. In severe cases, the fiber can just snap.
So you absolutely cannot just sharply turn a corner with fiber like you might with electrical wire.
Definitely not. And the acceptable radius actually changes depending on the situation. Industry standards, and FDOT specs specifically reference these, define different minimums. Typically, there are two main ones. Loaded, which means while the cable is under pulling tension during installation, because of the added stress, the minimum radius is larger, usually 20 times the cable's outside diameter, OD. Unloaded, which is after installation when the cable is just resting in place, like in a conduit or tray. Here you can generally have a slightly tighter bend, typically 10 times the cable's OD. And FDOT even specifies a slightly different radius for long-term storage coiling in pull boxes or splice vaults, often 14 times the OD, to be extra safe over time. You always calculate this based on the cable's actual outer diameter.
20 times diameter when pulling, 10 times when resting, 14 times for storage.
Yeah.
Okay, always need to know the cable OD and the situation. Crucial for installers.
Crucial. Violating bend radius is a very common cause of problems in fiber installations.
This brings everything together perfectly. We've covered the tech, the reasons, the components, the types, the handling. So let's connect it directly back to our source context. What does the Florida Department of Transportation specifically require in their projects, pulling from those manuals and specs Atkins-Reales highlighted?
Right. This is where the general knowledge meets the specific rules for FDOT work. Their documentation is quite clear. First, the FDOT Design Manual, FDM, Section 233.5.1. It explicitly states that all ITES applications must be designed using single-mode fiber. No ambiguity there. It also mandates a minimum fiber count for new backbone installations. 144 single-mode fibers. That ensures plenty of capacity for current needs and future growth.
Okay, single mode mandatory, 144 fibers minimum for backbones. What about the cable construction itself?
That's covered in the standard specifications, Section 633. It specifies the use of loose tube single-mode fiber optics. And importantly, it often calls for low water peak, gel-free construction nowadays. It confirms the fibers themselves must meet certain performance standards, often referencing 1550 nanometer single-mode capability. Section 633 also reinforces that buffer tubes contain 12 fibers each, following the TIA 598D industry standard color code, which must be used in all installations. And critically, it reiterates those minimum bending radii, 10 times the OD unloaded, 20 times the OD loaded.
Loose tube, gel-free single mode, 12 fibers per tube, TIA colors, 10 by 20x bend radius, very specific. What about inside pull boxes?
Yes, there's a spec for that too. Standard specifications, Section 635, which deals with pull boxes and splice vaults, adds that crucial detail. Fiber optic cabling coiled for long-term storage inside these boxes cannot be bent tighter than 14 times the cable diameter. So you see how FDOT takes the general principles and sets very concrete requirements for contractors to follow, ensuring consistency and quality across their statewide ITES network.
Wow, that really ties it all together. What a comprehensive deep dive. Just to quickly recap for everyone listening, we hit our three main goals. We dug into how fiber optic technology works, those pulses of light representing zeros and ones, bouncing down the glass core via total internal reflection from source to destination. We explored why FDOT uses it, the huge advantages in speed, distance, bandwidth, reliability against interference, and security compared to copper. And we detailed what cabling is typically used, breaking down the components from the tiny fiber core, cladding and coating, up through buffer tubes with their color codes, and looking at different cable types like the loose tubes specified by FDOT, plus armored and aerial, and the crucial concept of minimum bend radius. It really gives you an appreciation for the precision involved, right? Starting with something as thin as a human hair and building this robust communication backbone. And remember, this was just Fiber Optics 101. The original Atkins-Reales masterclass for FDOT goes further. There's a 102 covering connections and hardware, and a 103 on design, testing, and installation. Lots more to explore there.
Absolutely. It's a field where meticulous work pays off. And maybe a final thought to leave you with. Considering how incredibly fragile these individual glass fibers are at their core, despite all the protective layers, and yet how utterly dependent we're becoming on the massive data throughput they provide, what kind of innovations are next? Maybe new materials or even smarter installation techniques to further protect these vital communication lines? Or how will the ever-increasing demand for data push the limits of even this technology? Something to ponder. And just one final crucial reminder, this overview, Fiber Optics 101, Basics in Cabling, was created and presented by Atkins-Reales specifically for the Florida Department of Transportation. Thanks for joining us on the deep dive today.